Hello, we start now the second part, the part 4.2 of this module of exergonomic iterative optimization. So we have seen so far the methodology, and we have individuated the most important variable to be taken from the thermoeconomic analysis, which are mainly the relative difference of the unit thermoeconomic cost between fuel and product of a component by component of the system, of course, and the exergonomic factor of every component of the system. So now the iterative optimization procedure can be, as I said, is a heuristic. It can be developed qualitatively in the following way. So the step could be: consider first, imagine you have several components in your system, can be 30 components. You put a list. Consider first the component with the highest value of the unit thermoeconomic cost of the product. So the component which have a very high cost of the product can be a signal of something which is particular. But not only, it's not sufficient, because even if the cost is high, maybe the cost of the product is high, maybe the cost of the fuel was already high, so it's not really a problem of this component. So what we have to focus is especially the component in which the relative increase of the unit thermoeconomic cost between fuel and product is very high. So consider first, in the previous list, the components with the highest relative variation of the unit thermoeconomic cost of the exergy flow across the component itself. So the one in which the relative increase is very high, this can be a suggestion of some problem arising, already existing. So at this point we consider that the relative increase can be due mostly to capital cost problem, so problem in the sense that there is probably in the framework of your system this component is too expensive, or on the other hand this component is too inefficient, so there is a too high amount of irreversibility and probably the component is too cheap. So this can be discriminated by making use of the exergonomic factor of the component that you are analyzing. If the component that you have in your list with a high irreversibility, increase of unit thermoeconomic cost, if this component has an exergonomic factor close to 1, maybe it could be worth to reduce its investment cost. So to change its component with one of a little lower efficiency, but with a better effect in terms of economy, because the cost will be lower. If a component, on the other hand, has an exergonomic factor close to 0, yeah, this is it could be worth to increase its efficiency, definitely. Probably this component is too inefficient and at the same time too cheap for your system. So this is a sort of list of steps that you can follow step by step in order to try to improve step by step the behavior of your system. You see, it's a heuristic procedure, it's not analytical like the one that we have already seen, but it can be interesting if you have to deal with a plant which already exists. So you're not designing from scratch an optimum plant, like we have done in the first part of the course. Here we are dealing with a plant which is already existing, and we cannot design it from scratch. We want to make use of the analysis to improve its performance. So the example in this case is the already existing system of the gas turbine. We know very well it. These are, as usual, the data, the technical data that of this system. We have seen several times in this module. These are the data of the streams of the system, so the air and the exhaust. And these are the data of, on the top, the data for water, for the steam which is produced inside the system in the intercooler steam generator, and in the bottom the data for the fuel, which is, you remember, purely CH4, so model of fuel, of course. It's not natural gas. Here again I have reported written again the stream by stream the value of the specific exergy of the stream and the value of the exergy flow of every stream inside the system. So multiplication of product between the mass flow and the specific exergy of the stream. Here I have listed, as we have already done previously in the previous module, in the classical optimization, I have listed the investment cost function of each component of the plant. So these are useful, I can say necessary to calculate the cost of the component when you change a situation. So when you change the point of operation, when you change the design of the component. So you modify the component, its point of operation inside your system. So there is the cost function for the air compressor. You see it's a function of the beta, so the compression ratio, for example. If you change in your analysis, you decide to change the pressure, the point of operation of the compressor, modifying the pressure ratio, you have to know how to modify, how this effect will modify not only the thermodynamic of the system, but also the cost of the component. So this is because this is why it's necessary to have the cost function of the component inside the analysis. So we have air compressor, combustor, the expander of the gas turbine, the air preheater, the cost of the air preheater related to the surface of exchange of the air preheater, and the cost of the heat recovery steam generator. These are in this table the fitting parameter of the cost function of the different component of the system under analysis. And in this slide I have reported the equation which usually we use to pass from the capital cost function of the component to the recovery cost of the component second by second. So multiplying it by the maintenance factor phi and by the capital recovery factor of my analysis, which is related, as we know, to the return of investment and to the number of years of operation of the plant. After dividing it by the number of hours of operation of the plant in 1 year, and the tau, which is the number of seconds in 1 hour. So in this case, I have used the 1.06 for the maintenance factor, as usual, as I have already used in some part of the course. And the capital recovery factor is 18.2%, which comes from a return of investment of 17.5%. The number of hours of operation in a year is 8,000 hours per year. In terms of operation cost of the external resource, in this case we are talking of the cost of the fuel. So the cost of the unit cost of the fuel is given by the market. In our analysis can be an external parameter, which the analysis obtained from the external market, and it is in my analysis 4 by 10 power minus 6 $ per kilojoule. So this is the cost that I have used to obtain my result. So these are the, I can say, the list of the steps to be done in order to make the analysis, the exergonomic iterative optimization, and all the data that we can use to analyze this classical example that we are developing during the course. So in the next part I will show you the result and some comments. So thank you for your attention.